thank you for inviting me attending this conference. I'm so glad to have this opportunity to share some of our research from my center associated with Chinese Academy of Sciences. Myself is a mathematics and systems ecologist. However, I have lead various team in US, in China, and in Europe to do several different things to make them together as the comprehensive deal with ecological issues, especially restoration and ecological engineering. So to me, looking at biochar is one way to the approach in ecological engineering deal with real-world ecological problem. So most material today I give talk is prepared by my student and colleague. They have the group, especially look at ecological nanomaterial and technology deal with major ecological issues. So myself is much broad. So I will start with my own part of research, then lead to why we have this need that to reinforce overall in a much broad scale, let's say, watershed ecological restoration. So some of I started with have Chinese, but later is pure English. Okay. So my research involved in the last 35 years or so. The major ecological restoration project in the United States is 4 of them. Each of them investment is all more than 25 billion US dollars. Okay, not more than billion, B, not M. So I involved the first 3. From that, what we recognize is the 6 major eco-technology or the methods for the ecological engineering is looking into first you need to have the structure, biophysical environmental restoration part. Then you have the use the vegetations, wetlands, all the different approach. But very, very important, you have 4 major factors. One, you need to look at the hydrodynamics part, microbiology part, soil, okay, so that's how the biochar play here, and the vegetation, okay? So I'm not going to detail other part. I want to mention overall in the watershed ecological restoration related with biochar, the soil, the plants, micro. So biochar, actually I worked with David Crowley back to 20-some years ago. I noticed Professor Oates mentioned the one reference have co-authored with Professor Penn. Actually, he is working in United States University with the David Crowley back to 20-some years ago. So David Crowley is one of the founding members for International Biochar Initiative at the time. Of course, now he retired. So that time we were working together for what project is about the BP oil spill, looking into the deal with the beach area, how to clean up and stuff. So from that, we also learned that basic or most important part component. So certainly have what we learn from nature, how to deal with it, and creating those overall biochar is part of the material we use for overall restoration practice. I jumping a little bit to look at a real case, probably you have a better idea. For example, even we used ecological restoration design. Let's say you're from the traditional approach, they just don't care, just use the directive from the structure, flat, whatever. So let's start the restoration practice. But if from what we have, the learn from nature, the resource design, if you look at biophysics structure, lead to habitat diversity, ecological functionality, biodiversity issues. And those are some of the cases we have done in Mexico, United States. You can see the basically what design is, and you see the restoration part. You can see the big bus right there, just give you an idea of the scale, how extent we can use that to look at a large scale restoration. And also have a lot of the material. So that part also biochar can play in those settings. The one of the case in China is in the Chongqing, the Guangdang, the ecological restoration. And also we have done with the what they call the south to north diversion, okay? To look at the Danjiang, the water reserve area. And the very important things I would like to show you is how we can design, of course, my long-term friends, and I'm doing the theory and the methodology. Then Dr. Yegang Wu down to nurse, realizing the engineering there. Okay. So that's how we have done, used if you look at it, that you have the engineering activity involved in entire restoration, but if you look at the outcome, okay, this is the before, this is the after, okay, the restore the natural setting. But the processes also involve the biochar related material we use to help to clean, get a better quality of the water. If you look at this as well. Okay. So that's kind of my opening from my own part. Look at much broader scale ecological restoration, how the biochar can play a role. Now I'm going to one of my students and colleagues in my center, since I talked in China so many times, I don't want to always talk my own stuff. So I would like to promote some of my team members. I have the center with the Chinese Academy of Sciences. They have a multiple different research team. One of them is dealing with the biochar. So I would like to talk about from this three aspects. But first one, I will very quickly skip because Professor Oak already gave a quite nice overview and introduction about the biochar. Okay. That's the kind of things I will move quickly. So by the way, I have two titles. Okay, another one is also honorary director general with the Three Gorge Institute of the Ecology and the Environment, Chinese Academy of Sciences. So I'm honorary. I'm not direct dealing with daily-based operation. So this part, I think Professor Oak already talked about it, and that's the general processes. I would like to mention that is when I work together with Dave Parley, we also use the biochar combined with the microfungus, and also plant root grows the material, because especially we live in arid and semi-arid environment, so we have to change the soil condition in order to have in a relatively dry land agricultural farming practice. And by the way, the biochar is not really new. If you look at 1,000 years of Chinese farming and many agricultural activity in the tropical regions, like Amazons, have, of course, not sophisticated like today, but this whole idea and the practice already in those farming practice, farming related activities. They're not moving. That's related with not moving. Okay, never mind. I just feel like to use this look at the for the water treatment. It's also used for the pollutants removal. So I would like to address the issue related from the agriculture and forestry waste and the emerging pollutants treatment technology used in biochars. The biochar, from that, we can look at advanced oxidation of emergent the pollutants. So what we're talking about is reduction, well, I cannot use the better, is related with the reduction of emerging pollutants. As you know, these days from the pharmaceuticals, even for to eat the meat, everything, the production practice use a lot of chemicals not exist in nature in the past. That kind of issue be recognized in the United States and the Europeans roughly in 2005. What we recognize, they have more than 3,000 emergent chemical species in our drinking water. Certainly today, have a lot of the research and want to solve those kind of problems. Still, we're facing a very, very tough challenge. So we have used Biochar-based biochar to help the reduction. So they have the 52% of world homologs produced in China. That means very, very rich material we can actually use. So that's why we choose that as the model system to study. So 45% of that is composed of these here. So we can see around the ratios, how the practice, processes, and degradation process and the pathways. And we have the photoplatelet degradation, the practice, use the material, and you can see the result is about 90 minutes. 90 minutes is about nearly complete removal. Because in our institute nearby, they have several major pharmaceutical companies. They have been polluting the environment surrounding. Theoretically, they should have something treated before release to city sewage systems, but most time they're not. So that's why we have this project that and also you can see the biochar restricted the recombination of the photo-generated carrier. So make that technique we use the simple and the economic. We also look at PMX activation for degradation of SMX, the project. You can see also the high level nitrogen contents, then have the fast and efficient, roughly 30 minutes, removed about 95%. Well, certainly they have certain structure and on the surface for the biochar characterization. And those are the key degradation factors abundant in active sites. And the efficiency is related with non-toxical intermediate. So that's practical for the application. We try to reduce the intermediate. Those may have the toxical to the environment. So have corn cob based biochar. As we know in China, that's a lot, especially like one time like the Shandong is everywhere pretty much. So the natural corn cob consists of epidemic layer. You have multiple of those layers. So those layers rough, uneven, and brittle, making that ideal raw material for biochar preparation. So you can deal with over 10 types emergent pollutants. And that's the diagram looking into the reduction of the emergent pollutants. And also, global outcome do not aggregate it on the carbon-based material, but dispersed as single atom. And also they coordinate with the nitrogen atom that is significantly bonded with peroxide nitrogen. So they have some good features. For example, they can have the best performance, achieving the 98.5, the degradation of the rate of fire within 10 minutes. And they have the reaction rate is roughly 0.444 per minute. And their leaching is low, also significantly lower than the limit value in nature surface water environmental standards. So what this means is the entire process is also certified with the environmental standard. It can efficiently degrade 10 emergent pollutants with the degradation rate all above the 75%. This is used still remain stable in the complex water matrix with minimum the influence from the pH, coexistence iron, and DOM. It's demonstrated good treatment effect for the water in buffer zones, wastewater from the sewage treatment plants, tap water, and the pharmaceutical waste waters. We have been working on the real case with nearby pharmaceutical company. So basically each of the results you can see from here, related with control and all the others. This portion is we look into the various situation and look at how we can primarily attack the site for the electronic species. You can see the chargers, adoption, energies, relationship. Some intermediate products, they could induce acute toxicity, growth inhibition, and development toxicities. So, catalyst that does not significantly alter the microbial community structure and abundances in aquatic environment. So that's also important that we want to maintain. Like I said, that's fundamental for watershed ecological restoration. You have to have the micro soil plants you need to maintain that. You don't want to alter those good have functional structure and abundances. And you can, same time, we can deal with multiple antibiotics. That's also important because we have these days many the antibiotic chemical species coexist in nature. So that's something related with degradation rate constant antibiotics reach to as high as 0.82 per minute, and the mineralization rate antibiotics exceed 60% within 15 minutes. We also can remove others all above the 80%. So synergetic effect, radical, non-radical pathway with the different to play the key role. Valent state transition of the iron animal, along with electron transport, can activate PMS to produce this. So then formulation, this can reduce the different form, then attack or accelerate it and formulate this diagram. So we also study the flow experiment, look at the various situations, look at the removal rate in the real water. It's about for each of the emerging pollutants, roughly about 94%, 90%, 89%, 82%. So gross toxicity experiment, we also did that work. Toxicity of the treated water to plants significantly reduced with the root length and the stem length being very, very close to those controlled group. So that's the very important part. We don't want to have that produce the toxicity during the whole processes affect the plant growth. The third part I would like to talk about biochar from the invasive plant biomass and the emerging pollutants treatment technology. As you know, in China have a very, very big challenge from the invasive plants, even in terms of topics around the coastal area. I don't know the English name, the Hupa Micao, right? That's on the one hand it's used for stabilizing the sands for the erosion, but on the other hand that's the invasive species. And in a large area that basically go wild and out of control. So that's another issue we have to deal with, how we can use something we needed. It's not good. We have to deal with it. On the other hand, how we can use that to creating something useful, meaningful, and helpful. So we looking into how we can, based on the invasive plant biomass, that's several invasive plant herbivores, those basically the weeds, widely distributed, abundant, at the same time aggressive reproduction and harmful to the crop production and the native vegetation restoration. A lot of restoration projects have failed because we have no way to actively control those invasive species. So what we can do is use advanced oxidation and remove those emerging pollutants, use those invasive plant biomass, processing them, catalysts, biomass-based catalysts. You have processing, so optimization, and lead to reduction of emergent pollutants. So that's roughly the idea of the deep and rapid degradation processes. And this we can look at, even the distributed on the biochar. If 3 minutes, very fast, 3 minutes, they have the kinetic constants equal to 1.8, efficiency about 100%. They have a high mineralization rate, strong adaptability in the various water samples we have done. And through the 5 cycles, we moved 90% and also the low leaching rate. And the synergetic degradation of dyes by free and non-free radicals. You can enhance the electronic mobility, accelerating the from the 3 to 2 the transition, and improve the degradation of the ions. Also, because you have this, the 4 pass can accelerating that kind of transition, further enhance the degradation of the ions. We have looked into the 2 pathways, 9 intermediates, and no obvious toxicity. That's also for the ecological restoration. We don't want to do in the process is to introduce additional environmental product. So that's during our design of the biochar process, the whole entire process is that's a key component we have to take into account. Finally, I would like to we propose the general approach to reduce the intermediate products and achieve the low or non-toxic outcomes. Have to be rapid, deep degradation. So we have been used invasive species, the plant biochar, the carbon nitrate formation, deal with the emerging contaminants removal. So this is 3 invasive species we use, especially in spiritual watch dam area, because the water fluctuation, they have like 30 meters, and each year they have some period of time, at least like 3 or 4 months. So that grows so fast. So we can actually use those plant species for that purpose. So both single metal and bimetallic species have been successfully loaded onto the biochar, and the carbon nitrate structure is formed on biochar catalyst. You can see that's for the single metal bimetallic. So we can achieve about 100% remove 6 emerging pollutants within 5 to 20 minutes. Bimetallic doping enhance the reaction rate of the biochar catalyst. So you can have that kind of involve the oxidization reaction processes all in the same time. Bimetallic doping change the reactive species composition, so they actually enhance non-red pathway. So if we take CIP as an example, then degradation involved the 3 pathway and 12 intermediates with P5, P8, P12, exhibiting potential toxicity. Then all three invasive species, invasive plant species biochar, catalysts show good performance, excellent recyclability, suitability for treatment of real world water samples. Well, that's something from my group, the work, since when I received the invitation, I look at all the talk about biochar, so I think the better use this opportunity to introduce even I'm not an expert, I involved and worked with the biochar people more than 20 years, but I as a tool, as the mean to deal with overall much larger scale ecological restoration, but that's always the one component in my entire research program. So when I saw that, I said, okay, you better prepare this talk for me, at least I can share something with the colleague actually working in this area, so then we can build up the future communication, exchange idea, and possible collaboration with the center, with the Chinese Academy of Sciences. Thank you.
Okay. Thank you, Professor. Are there any questions to discuss with Professor Larry Lee? Okay.
Yes, thank you, Professor Lee. And I would like to ask a question with co-headers. Yes, we focus on the hydrodynamic and hydraulic. So, you mentioned the leaching rates. So I would like to ask the hydrodynamic factor during the micropollutant contact with biochar carrier. So, in what kind of the hydrodynamic condition, for example, the velocity of the flow, during what kind of these circumstance could make these reaction be stable for the biodegradation? Thank you.
Okay, that's an interesting issue. Frankly speaking, we have not done that specifically for biochar. However, I can answer your question from my early experience back to early 90s. I have been working with Argonne National Lab with the U.S. Department of Energy. We specifically studied that part of things, especially for nuclear waste site design. So that depends on the soil structure, and also the micro and other environmental factors. Traditional modeling for categorizing the leaching rate of processes, all based on the Euclidean space, that kind of just simplify the calculation. But reality is, let's say, if you're leaching, the material have some kind of organic matter. You have the microbial population around. So that have the use this as nutrient source for growth, death, the kind of dynamics. So if they dead, then block those porous media structure. Actually, your leaching is very difficult to pass through. So what your modeling approach characterizing the leaching rate no longer just simple in a uniform, the pure same size particles or fine sand, the kind of setting that become the fractional space. Then entire equation structure you have to rewrite it. If you're interested in that, you can check my early 90s publication related with how to calculate, including the probability of the for the bioremediation of the microbial that's evaporated.
Thank you.
Okay, are there any questions? Oh, very good. Our young professor.
Oh, good.
Hi, Professor Lee. I have an initial question. I noticed that you use a lot of biochar, using it as a candidate for the preparation of a lot of catalysts for the activation of PMS. We know that biochar is a great candidate for the preparation of numbers of catalysts, but the biochar poses a lot of surface functional groups. How do we locate it or identify the main active sites during the activation process?
Well, frankly speaking, I do not know. But I can pass your question to my assistant because I'm not lab person. They did all the lab work. So I'm sure they will be able to answer that question.
Thank you very much.
Yeah, sorry about it.
Okay, thank you. Any questions? Oh, very good.
Hi, great. This is Fang Jie from the Institute of Soil Science, Chinese Academy of Sciences. So I'm very interested in the ecological restoration project you have done. So I'm wondering, because you are doing the large-scale catchment restoration, mostly you're having river, right? So in that case, I'm wondering, the more focus is on the bank, the riverbank restoration, or you also did the water quality treatment, like any contaminant on the bank, around the soil, and any contaminant in the river you have also remediated?
Yes, like I said, most of those model and the methodology I developed, but the Dr. Yegang Wu, put that to the real case. We have been doing this hundreds of projects in the United States and in China, quite successful. I show you the south to north, the area, Danjiang, the water source reserve area. Even we designed 2014's complete engineering project in 2015. This year, the late September, have some group ask me where can see the demonstration, what we have done. I told them where the location, the group went there, checked the water quality, still maintain exactly where designed. Even back how many years, about 10 years ago.
So, what kind of contaminant around the river, in the river and around the...
That one is a water treatment plant. They actually, well, for the, this particular, because the water need to transport to Beijing. So the central government have very, very strict the regulation, the policy. If local government cannot achieve reach to the basic standard, then they have to remove those top leaders. So that's why they are very serious about that. So that time we designed the entire area watershed. However, they have a lot of interested group and they're very powerful. So they don't want you make all the money. So what they did is to the end, we only realized our design in one river, Sending River. Because I have a whole bunch, that's most pollute the river with most water treatment plant in that region. So as you know, the water treatment plant that come out of the water still, theoretically, you have no plant really can grow. So what we designed is from ecological engineering. That's why the biochar, all those play a role here. Okay. So we designed the ecological engineering project as the entire processes and made the water treatment plant the water eventually before reach to the river, going to this reservoir, reach to Chinese standard third category 3, water standard, all those numbers.
So it's like adding another step of deeper treatment before we discharge the water from
Right,
the.
right,
Okay.
right.
Okay, I see. So how about the bank, the restoration? You designed biochar in the.
Inside some specific locations, because we also need to have those quickly for those vegetation establishment. So the original soil condition is not really that good. That's why I showed on one slide to look at how you can actually construct and embed, including the biochar, those material, very quickly you revegetate the whole area. Otherwise, it will not easily stable of the entire.
Okay, so that's for some areas. So I'm wondering, because if we want to restore a very long bank, I mean, can we afford?
Well, that's another. Well, we have a theories, the engineering solution for that, but needed based on each circumstances. Not about all of it. For example, the Guangyang Island, only portion of that used our approach, another portion used others. But of course, that's government that usually they don't want to take risk. They want to put everything there, so then no one say some bad words. Everybody have some money. That's different things. There's more politics. But to me, I think that we have offered a better solution. But we see.
May I know the cost of the voucher you applied on the bank, river bank?
Yeah, the reconstruct the different layer. Okay. For example, you have different rock size and biochar, and the soils. You several different layers in the mix. But
yeah.
not all biochar. No.
Yeah,
Okay, no.
so you must, for the project, you must produce biochar in large scale.
Yeah,
So,
well, they have
talking
a
about
large
that too.
scale production.
so what's the average cost for 1 ton of biochar?
Sorry, I do not know. I'm like I said, I'm doing the methodology and the modeling. I'm not tell them what's the proportion. Then you see that's why I'm not in the picture, when the Dr. Wu, direct all the engineering stuff, I trust him because we collaborate about 40 years.
Oh, okay, thank you.
Thank you.
Okay, thank you.